Thanks for having me here. So, uh, the company that I'm representing, High Space Technologies, uh, we work on bringing very well-known terrestrial technologies into satellites, and we are more of solving the engineering problems. The application is something that I may not touch on much, but I think some of the other speakers are already speaking about them. So I'll just get into some of the problems that the remote sensing engineering side faces, and probably one best way to look at it is to see this picture, which is typically remote sensing generates a lot of data almost every day. And data centers are a key to uh, getting all this information processed, bring them to users, both application scientists as well as sometimes end users. End users are also probably streaming data onto their mobile phones, onto their dashboards, wherever they're making those decisions. So the paradigm that we've been in so far has been to download all the data that a satellite generates, and that's probably not very sustainable in the way that there's a lot of data, more than 90% of data, especially in the commercial side, which is never looked at. All of that data is still kept in the data centers, archived, and over time they end up going into long-term archives to sort of save data center costs. But one of the paradigms that is slowly coming in from industrial IoT is to download only what matters. This is event-based data extraction, event-based storage, event-based processing. And this is a new paradigm. We're not telling that this is what everybody should do, but this paradigm has to be respected for what value it can bring to certain application areas. And if you try to put some numbers on two sides of this, one is data generation. That data generation today is reaching way beyond 100 terabytes per day, being generated across all government, uh, civil, defense, uh, commercial, which is both optical, microwave, thermal, even sounding, weather data, all of that. We are increasing that data generation per day, but our capacity to bring all that data down is growing at a very linear pace. And there's a huge gap. And as of today, that gap is 600%. And we have to have ways to deal with it. It's just that everybody thinks making the sensors is very cool, making satellites is very cool. We've put more than 6,000 satellites up in space, but we don't have enough infrastructure on the ground to process all of that. And if we want to match the pace at which the data is being generated, I think we need to think in different ways. So one of the ways to think about this is rather than being bogged down by the deluge of data, think about them as a streaming source of information. And if you can intercept that source of information with your own needs, so say I want soil characteristics from the data, and as the data comes in, I put in a rake, just like how you put that for like fluid dynamics experiments, and tap out only that information that is necessary for you and you have user base, and start extracting that information. And this is very critical when you come to disaster, you're coming to national security events, where today the satellite is dumping terabytes of data per day to data centers. It's being processed with some delay because still you don't have enough capacity to bring that data down in real time. And then finally, you're going to find that, okay, something's happened. I need to respond. But you've already spent more than a day between data generation and taking that action. There are, of course, a lot of edge cases where this data can come down much faster, and those are for very high value applications. But what happens is when that is being served, all the other users, all the other use cases get compromised and pushed back into the queue. So this is the exception, not the norm, that you can beat this 24-hour clock. Now, proposal is to adopt newer technologies, which is bring more processing onto the satellite and be able to derive that actionable insight directly and then push that down to the ground. And pushing that down to the ground, of course, has a lot more technologies that you want to integrate. So you may be wanting to bring direct to device communications. You may be wanting to bring inter-satellite communications. There are a whole host of things, but one of the parts is just to be thinking of processing not just at the data center, but bring more lightweight software that can run on the satellites themselves. So this enables more direct action, and you can at least get enough information at a high sampling rate. Now, this is another way to look at it, which is from a computational side, is you bring the processing into the satellite, and you're able to not just sense, but also uh, infer. And that could give you the ability to detect an event. And now, in the case that an event is detected or not, you can choose to discard the raw data. And this is a very touchy topic. A lot of scientists don't like it, but a particular type of scientist who really wants this outcome is ready to discard, because the alert and download, you would really want to prioritize that because you want more of that. And to increase the capacity of that, you will have to discard something. So if we start thinking more about the engineering problems, we'll start having to make these compromises. And those compromises actually will push our industry forward. So there are a lot of advantages. So when you discard, you're saving bandwidth, you're reducing storage on the ground, also on the satellite. And you're starting to focus on the value, which is down. You can notify immediately, selectively download what you need, and you can start enabling rapid response as a rule, not as an exception. There are some very high level application examples I will share. So one of them is the maritime traffic and illegal, unregulated, unreported fishing. Uh, and if we look at the global map of maritime traffic, it's all over. As in, the navigable part of the ocean is much larger than what we can see. But when you just look at maps like this, you can go to any of these open source marine traffic websites. You see that the traffic is in places that you can't really get even satellite images for. And just to try and experiment this, I went ahead and took the whole Sentinel Landsat optical archive to see its coverage. So all the white areas that you see, you almost can't see it because it's not covering the open ocean. It's very close to land. That's the coverage. You include even say Sentinel-1, which is microwave. It doesn't really increase by much, and the only advantage of Sentinel-1 is that it's radar, and you can see when there's cloud cover, you can see at night. So that's the net total of what we are monitoring almost every once in a week. And those huge gaps that you see, I'll just sum them up as in just very approximate economic areas of interest. And that that itself is close to 150 million square kilometers that is not being monitored. And this is not just from a national security angle, because most people really think, hey, illegal stuff is going. It's actually overfishing. You can imagine all the places that we're not able to see, there is certainly overfishing, and we have no clue about it. And the only sensors today that we have are shipping uh, ship tracking radio. And many of these illegal fishing vessels are not choosing to keep the radio on. They just turn it off. So they know where they are. You do not know where they are. Even if you're another fishing vessel right in front of them and there's a lot of fog, you might just hit into them, or you might just lose all your fish. And these are some numbers just to consider that the navigable area, half of that is blind. Uh, Somewhere in that Venn diagram is the economic responsibility area of a lot of countries, and even they do not have resources to monitor this, purely because it's very expensive in the current paradigm that we have. Here's another application, which is to aggregate a lot of disaster monitoring. These are what I call as low probability events, spatially dispersed, and it makes absolutely no sense for any commercial undertaking to monitor all of this in a timely fashion. If you start bringing decision making into the satellite, you can start doing that. You can start detecting events as the satellite flies. As it's imaging continuously, you can start saying, hey, this is an interesting event, alert, this is not interesting, nothing's happening, delete the image, and keep going on and on. And what this can enable is a lot of satellites working together to solve problems on Earth. And that potential has not been unlocked. A lot of people have been thinking that we put a lot of satellites sum total of them should be like solving problems, but no. We may be having 6,000 satellites, but they're all working as 6,000 different entities. Here is something that's more on the computer vision and core data quality uh, angle. So in 2017 and almost ending in 2019, uh, I think Samsung, Google, and to an extent Apple, they brought in some very great uh, features to their phones, and those features were not more cameras. In fact, some of these companies have started to reduce the number of cameras on their phones. And the reason is this term, which is not often brought in remote sensing, is computational imaging, which is to be able to get more quality, fidelity features out of images without pushing your hardware beyond a particular element, because that brings cost. So what you can do, and if your camera is capable of oversampling, you can always get more information. But the problem is now you can't oversample. We have already spoken about having 6 times less capacity. You oversample, decide on which of those samples is the best, and then bring that down, or even do fusion to get the best of all of those samples. So computational imaging for remote sensing, how that might look. This is just a proposal. Of course, some parts of it many people are already working on. Is and this is an example for a frame-based uh, multispectral imager. So today, what you're doing is take a single frame, say there's some size to that, we just put that number there. The data comes down, you process it, and you get some okay quality data. On the other side, if you start using the way these smartphones start working is, say you do an oversampling by 4 times, data size goes up. You have to bear that cost, uh, but now you bring down that data size by processing that on board. So say you can pick a GPU, put some sample specs or an FPGA, and that's the basic spec. So at 8 to 10 watts extra power, you can get a smaller size image which has better compressibility purely because you're eliminating some of the noise. Uh, the data quality is actually going up non-intuitively. And now you bring that down, do post-processing, and you get much higher quality data. And this is something that we've attempted to replicate for satellite data. It's very encouraging. The key thing is that somebody has to accept oversampling. So yeah, so there's a lot of improvements. Empirically, we've been able to get SNR improvements, less downlink volume. Ultimately, you're able to do the same things that edge computing can. This is another case where collect more data on board, but bring down less data. But what's there in the middle is more processing. So you have a hyperspectral imager, which is obviously going to generate a ton of data. You have a higher resolution, but lower spectral resolution imager. What can it do? It could probably detect signatures for materials. And you can just bring down the shape file or the boundary or even area estimate of what it's looking for without bringing in all the data down. And the way we've gone about solving some of these problems is to have like a whole library of building blocks that can solve small problems, and then plug and play whenever you need them in whatever fashion that you want, like a graph sort of processing. Here's an example of something that we did. So our software is flying on 2 satellites currently, and that's one of the sample inputs to our processing. And in a few seconds, the result is a very low fidelity land use mask, because again, we don't do applications, so we've done probably the most basic thing, which is vegetation, no vegetations, as in scarce vegetation and water body. But the interesting thing here is that the satellite keeps taking images, and we keep discarding images that have like more than 80% cloud cover, just as a demonstration to say how much data that we can save. Uh, what more can be done? And this is the food for thought for everyone who's looked at a lot of remote sensing data. What you can see on the left hand side is images taken of the same spot in the sea over time. And you can see that even though the sea we know is supposed to be blue, it looks very different under very different lighting conditions. And normalizing that to do object detection or even extracting ocean color is very hard. can we solve some of those problems using onboard processing or even computational imaging? There's another common thing that some of those problems are solved by tiling. And you can see when you tile and you process the images, it's not like the beautiful Google base map. It actually looks like this. Some parts of it are amazing, some parts are not that great, but all these images are taken in the same pass by the satellite at roughly the same time. And they look very different. It's very, very hard to normalize them, especially when you start using machine learning, artificial intelligence. By hand, you can actually start tuning them, but can you tune it for the whole world? So I'll end with another picture. So this is an image taken of the coast of Andhra. This is optimized for land monitoring. Physically tweak it to monitor the sea. You look at this and it's overexposed everything on land and the clouds are looking bad. So this is the manual effort that people do. You can of course automate it, but this is not really scalable. As in, are there ways in which we can standardize these sorts of data so that ultimately we are able to get actionable real-time insights uh, in the future? So thank you and open for questions.